Welcome to the fourth lesson of the Plutus Pioneer program. This one is going to be mainly focused around off-chain code. We start with a conceptual overview of the roles and characteristics of both on-chain and off-chain code in smart contracts. Then, Luca is going to present a graphical user interface for the Cardano CLI he prepared so you can have a more interactive way of exploring the tool. And finally, Thomas is going to show you a bit more about Kuber and Lucid. Let's get started. Not so long ago, we had just one way of coding smart contracts. Now, in less than a year, several new options of both on-chain and off-chain code popped up all around the ecosystem. Knowing how to use specific tools is important, but understanding the concepts behind those tools is arguably even more important since it allows you to quickly adapt to technology changes and move between tools and languages as needed. Okay, let's get started. Since we're in the fourth lecture of the Plutus Pioneer program, I'm going to assume you know how the extended UTXO model works and that you've written and used a few simple smart contracts. Okay, so what do we mean by on and off-chain code? When we talk about on-chain code, we mean code that runs in the node during the inclusion of new transactions and data that is stored in the blockchain. We're going to talk about it in detail in the next slides. But on-chain code is basically the transaction itself with its inputs and outputs, etc., and the validators that check if you can actually perform the transaction. And when we talk about off-chain code, we mean code that runs in the user's or a service provider's device to query the blockchain, build and submit transactions. This can be a step-by-step process, but you can also do complex stuff. For example, you could have a running process to check the state of a transaction and show it in a UI. Or one that tracks an address and submits transactions when a specific UTXO is consumed or a date passes. Keep in mind that the blockchain is a passive entity. It doesn't do anything by itself. The only way something happens on a blockchain is if someone sends a transaction. Most of the code is off-chain code, which is great because that's code that doesn't run in the node. We can easily change it and it doesn't need to have the same performance and security standards on-chain code has to have. If your validator logs 10 million ADA, you better be sure that it works as expected. But if your transaction tries to consume some UTXO in a way that the validator doesn't allow, it would just fail and you can try it again. That doesn't mean that you can goof around with off-chain code. But if there's something wrong with it, the security of your validator is not affected. Which brings me to the next question. Why is it necessary to decompose our code? Well, because both on-chain and off-chain code have inherent advantages and limitations. On-chain code ensures integrity, but it's expensive. And off-chain code doesn't ensure integrity, but has access to the user's wallet and resources. What I mean by expensive is that all the data in the blockchain has to be synchronized and validated in all the nodes, at least until Mithril is live. Plus, all code that runs on the blockchain has to be paid for. We want our blockchain to be as fast, lightweight, and affordable as possible. So we move as much as we can to the off-chain side of things. As we saw previously, the validator contains logic that is enforced to make sure only transactions that meet those obligations are successfully validated and added to the blockchain. Because the script's integrity is crucial, we store it in our cryptographically immutable blockchain to prevent bad actors from modifying it. That's why the script needs to be on-chain code. But to get to that stage, first we have to query the blockchain to find out which UTXOs we want to consume. Then construct the transaction with those UTXOs, the redeemer, and everything we need. And finally, we want to sign and submit the transaction so the node can validate it. All that requires a lot of resources, depend on the user's choices, and crucially, it requires the user's signature. Even if it's not required by the validator's logic, the transaction needs to be signed to allow it to spend at least one of the user's UTXOs. Because of all that, and because we don't need assurance of integrity, we do those tasks off-chain. Okay, now let's take a deeper look at on-chain code. This is the compiling pipeline our code goes through to become something a node can run. We start with Plutus TX. This is the high-level language developers use to code the script. You've used this before. Then, when we compile this code, it goes through several steps. First, it gets transformed to GHC core. This is part of GHC compilation pipeline. Then we take that and compile it to a Plutus intermediate representation. From now on, we're independent of GHC and Haskell and have total control of the compilation pipeline. Then we transform it to Plutus core. This serves as an intermediate form that the compiler uses to statically check the program. And finally, we get to untyped Plutus core, which is what the node actually runs to validate the transaction. This language is really hard to code in directly and usually stored in binary representation. Why so many steps? Well, it's wise to break down big compilation pipelines by introducing intermediate languages or intermediate representations to ensure no step is too large and to test each step independently. But we, as Plutus developers, don't care much about the intermediate steps. The important thing is that what is run on the chain is untyped Plutus core. So you could theoretically use a different high-level language if you have a compiler that compiles into either one of those steps. And that's what members of the communities are doing. By replacing parts or all of the compilation pipeline, the community is coming up with libraries to code validators in other pre-existing languages like TypeScript, embedded domain-specific languages like Plutarch, and completely new languages like Aiken. Okay, cool. So we have this untyped Plutus core. How do I give it to the node? That's when the off-chain code comes in. And I will provide Cardano CLI's commands on the left to put you in context based on what you already learned in previous lessons. But this applies to all off-chain tooling. Let's start with querying the blockchain. This one is pretty self-explanatory. Unlike Ethereum smart contracts that have access to the state of the whole blockchain, Cardano validators have access only to the information related to the transactions we are making. That means the context of the transactions we want to submit, all its inputs and outputs with their respective values, datums, and scripts, and the actual redeemer. So if you want to consume a specific UTXO, access a specific datum, or use a script, you have to indicate them as part of your transaction, which means you have to find them first. And there are many ways to get this information. Of course, one is running your own local node, but also you can have your own local database that is synchronized with a local or remote node, usually through a chain indexer. Chain indexers follow the blockchain and store its information in databases. There are many different ways of doing this, and you have plenty of tools to choose from. Depending on the needs of the project you're working on, you might prefer one or the other. And finally, you can just use any third-party tool that runs its own nodes and databases. The upside is that you don't have to have anything on your computer. The downside is that you might be sacrificing speed, functionality, or security. So, again, it depends on your project's needs. Once you have everything needed, you can build your transaction. We'll look at the two most common scenarios when dealing with spending scripts. A script that validates if you can spend a UTXO. Scripts can have other purposes like minting and staking, but we'll have specific lessons for that. Let's start with how to deploy the script. Assuming we have the script serialized, as we saw in the on-chain part and previous lectures, first we have to get the script address. We can do it, for example, using the Cardano CLI with the address build command. This is something we have to do only once. And of course, with other tools, you might not need to do it even once because it can be derived automatically. Now that we have all the data needed and the script address, we can build a transaction to deploy it. Besides what I'm going to talk about here, and depending on the tool, you might need to indicate the era, the network, the name of the object or file where the end result is stored, etc. That depends on the specific tool, and it's not relevant to understand the concepts, so I will skip those details. So, as I said before, to build a transaction, we have to provide all the inputs and outputs, which in this case, the minimum input we will need is any UTXO owned by the signer that has enough value to pay for the transactions and whatever is locked with the validator. And the outputs should be at least one at the script address and one at the signer's address, or the address we want to give the change. Now, when we provide the datum of our script's UTXO, like Lars said in the first lecture, we have three options. One is to provide only the datum's hash in the output. The other is to provide the datum hash in the output, but also to include the actual datum in the body of the transaction. And finally, we also now have the option of providing the actual datum in the output instead of the datum's hash. Which of these options to use is up to the use case. For the producing transaction, the one we're doing right now, the main difference is cost. Putting the actual datum in the blockchain is more costly. But the real difference is for the consuming transaction. We'll learn about that in the next slide. But before that, we have a similar case for the validator's script. When providing a script, we have two options. Providing only the script hash, which is the payment part of the script address. In this case, we don't provide the actual script anywhere. That's the job of the consuming transaction. And the way we know that the consuming transaction didn't alter the script is that if it did, the hash will change and the transaction will be invalid. As you can see, when deploying the validator, the actual script is optional because we're not using it yet. Spending scripts care only about spending transactions. And because now we're not trying to spend but to create a script UTXO, the node doesn't need to run it. The second option is to attach the script to a UTXO. This is more expensive than the alternative. But if you are anticipating using the script a lot, it might be worth it, since the consuming transaction doesn't have to provide. To the left, I'm showing two different ways of building a transactions using the Cardano CLI, build and build raw. The difference between these two commands is that build automatically balances the transactions, and build raw requires you to do it manually. Manual coin selection, meaning choosing which UTXO to spend, calculating the fee, and balancing the transaction, making sure the inputs, outputs, and fees add up to zero, are great for learning purposes. But when you're working in something that has to run in production, you need some automated way of doing that. That's when coin selection and auto-balancing algorithms come in handy. These algorithms do all that for you. And tools like Mesh.js, Lucid, and others do this automatically. Coin selection, calculating the fees, and balancing are part of all transactions, so from now on, I'll skip mentioning it. That's conceptually everything you need to know to deploy your validator with any off-chain tooling of your choosing. Now, let's see how your choices here affect how you write your off-chain code when using this validator. Same as before, we have to indicate the inputs and outputs. But we also have the option to use reference inputs. We could have used reference inputs when deploying the validator, but we didn't have a reason to. Now we have to run the validator and it has to succeed to allow us to consume its UTXO. And that validator might require more information than the one available in our inputs. For example, it might need to check the current value stored in a datum of an oracle. In that case, we can provide the oracle's UTXO as a reference input to access its logged value and datum. The key difference of reference input is that we're not consuming the UTXO. Thousands of scripts can reference the same UTXO at the same time, and we don't need to be the ones controlling it to be able to reference it. This, combined with inline datums, is a powerful way of sharing information on chain. Now, the way we provide the datum depends on how the validator was deployed. If we want to consume a UTXO in the validator's address that only has the datum's hash, we have to have some off-chain way of knowing the datum, like a website or asking the person that deployed the script. This is not the best user experience, but there might be use cases when you prefer this. If we want to consume the UTXO that not only has the datum's hash in the output, but also the actual datum in its body, we can use a tool like a chain indexers to find and extract the datum. This is also far from ideal. Yes, the datum is on chain, but retrieving it is not easy. If you want to put the datum on chain, inline datum is likely the best choice. And finally, if UTXO has the datum as an inline datum, we only need to indicate that that's the case and the script will have access to it. Provided the script is a similar story. If we didn't attach the script to a UTXO, we have to have some off-chain way of knowing the script so we can provide it in the transaction. Same as when we only have the datum's hash. If we did attach the script to a UTXO, we could reference as a reference script, and it will have to pass to allow us to submit the transaction. This has several advantages. One big advantage of using this method is that scripts used frequently are not repeated over and over in the blockchain, making for a leaner blockchain overall. Another big one is that it helps to control transaction size. This makes for a cheaper transaction, yes, but also allow us to combine multiple reference scripts without reaching the maximum transaction size as easily as we would if we had to provide all of them in one transaction. Now that we are consuming the script's UTXO, we have to provide the redeemer. This is the responsibility of the consuming transaction because the producing transaction has no idea of what the consuming transaction will provide as the redeemer. So now's the time when we choose and provide the redeemer to the corresponding input. And lastly, we have to provide the collateral. The collateral is just an UTXO with enough ADA to pay for the execution of the transaction. We are running a script now, and the possibility of failure exists. In that case, we have to provide the node with a way of getting paid for its work. The collateral is not consumed if the transaction succeeds. only if it fails in a very specific scenario we'll explore when submitting the transaction. And that's it. As you can see, the way the script was deployed affects how we use it. So you have to think about this beforehand. For any of the two previous cases, we'll end up with a build transaction. But we cannot send a transaction to the blockchain because all transactions must be signed by at least one key. That's because every transaction has to spend at least one UTXO, and whoever owns the UTXO has to provide its signature to be able to spend it. This is the only step that can be done only at the user's device. We could have done all previous steps on the user's device or our own servers or at a service provider server. But the user's credentials should be stored locally under the user's control and in a cryptographic wallet like NAMI, Ethernet, Lace, etc. You will have to provide a way to connect your off-chain code with those wallets to allow the user to sign the transaction. We saw examples of this when Lars used Lucid with NAMI, and we will see more examples of this in future lectures. Finally, once we have our transaction signed and ready to go, the only thing left to do is to submit it. The act of submitting is simple, but what happens under the hood is not. When submitting a transaction, it has to pass two validation phases before being added to the blockchain. This two-phase validation scheme is designed to minimize the resources the nodes use to validate transactions, while also eliminating unexpected costs for the user. The first phase does multiple checks to know whether the transaction was built correctly and can be added to the ledger. For example, it checks if its inputs refer to UTXOs that actually exist on the ledger. Also, if it pays the correct amount of fees and provides the correct amount of collateral. If all the hashes are correct, if it includes all the data required for executing your Plutus scripts, etc. Basically, phase 1 checks everything except if the scripts validate the transaction. If this phase fails, the transaction is rejected without being included in a block, and no fees or collateral are charged. This is work the node did not get compensated for, but it's a tiny amount. And if this phase succeeds, the node can then perform the phase 2 validation. Thanks to phase 1, the node knows that it has everything needed to run the scripts and get paid. But it doesn't guarantee that all of the transaction's actions are processable. In the second phase, the node runs all the scripts included in the transaction. In today's examples, we have only one, but we could need to run several scripts in a single transaction. If the scripts validate all of the transaction's actions, the node will add the transaction to the ledger and collect the fees. If just one of the scripts fail, the whole transaction fails. But because running Plutus scripts can be computationally expensive, the node collects the collateral and ignores the rest of the transaction. This is why we have a collateral. And this is also why we indicate which input is the collateral when building the transaction. These are special inputs that have to have enough ADA to pay for the fees, no tokens, and cannot be in a script address. And because these UTXOs are only consumed if phase 2 fails, you can use the same UTXO over and over. Now comes the cool part. Let's talk about determinism. Determinism ensures that whenever a transaction is accepted, it will have predictable effects on the state of the ledger. Applying a transaction in the extended UTXO model is deterministic. And combining that with making sure that the script will always terminate and return the same result when applied to the same arguments, like a pure function, that the transaction fixes all the script's arguments during validation and specifies all the actions that require script validation, and that we have mandatory signatures on all transactions to ensure that they cannot be altered, we get deterministic script evaluation. All this is already part of Cardano's way of processing and evaluating scripts and transactions. So you don't have to do anything special. You get it for free. And in practice, this means that a user can run both validation phases and predict locally off-chain how much the fees will cost, if the transaction will be accepted, and the transaction's impact on the ledger. So users acting in good faith will have no surprises and should never lose their collateral. And that's pretty much it for now. As a side note, and for completeness, by the very nature of the vast majority of blockchains, there is this concept of forks and rollbacks. Sometimes the chain splits in 2 or more forks. It's not a big deal, it's part of the normal operation of a blockchain, and the consensus algorithm has a way to deal with this. But the block containing your transaction might end up in the wrong fork and not as a part of the chosen blockchain. It will be advisable to have an off-chain mechanism in place to deal with this case. Although it's not something you should worry about at this stage, because it will be easy to handle once you feel more comfortable with off-chain code in general. Okay, I hope this overview helped you better understand what is going on when writing your own and off-chain code. Let me know if you have any questions and I'll be happy to answer. Happy coding!